Chapter 1. The Chemistry of Autarky. In 1916, during the height of the First World War, Germany did not run out of ammunition. It did not run out of men. It ran out of rubber and nitrates. The British naval blockade strangled the German economy, cutting off raw materials from overseas. When the Nazis came to power 2 decades later, they remembered this lesson vividly. They looked at the map of the Third Reich and saw a geological trap. Germany had iron and it had coal. But for a modern mechanized war, it lacked the most critical component: oil. In 1938, Germany produced barely enough domestic crude oil to cover a fraction of its peacetime needs. A war requires roughly 20 times that amount. The German High Command faced a binary choice: either conquer the oil fields of the Middle East immediately or rewrite the laws of nature. They chose the latter. They turned to the engineers at IG Farben, the colossal chemical conglomerate. The solution lay in a process developed years earlier by a chemist named Friedrich Bergius. The theory was deceptively simple. Coal is a hydrocarbon. Oil is a hydrocarbon. The primary difference is that coal has too much carbon and not enough hydrogen. If you could force extra hydrogen molecules into coal, you could liquefy it. You could turn a solid rock into high-grade aviation fuel. But the engineering required to achieve this was terrifying. To make the Bergius process work, engineers had to build what were essentially massive pressure cookers. These were not standard factory vats. These were hydrogenation reactors, towering steel columns that had to operate at nearly 500 degrees Celsius. More critically, they had to hold that heat under pressures reaching 200 atmospheres. Later in the war, newer processes would push this to 700 atmospheres. The chemistry inside these vessels was a constant battle against the coal itself. German brown coal is dirty. It is rich in sulfur. In a standard reaction, sulfur poisons the metallic catalysts, coating them and stopping the chemical process dead. To solve this, IG Farben chemists couldn't use standard nickel catalysts. They had to develop exotic sulfides of tungsten and molybdenum, rare metals that were themselves hard to source, just to keep the reaction alive. For the architects and structural engineers of the time, this was uncharted territory. A standard riveted steel tank would explode instantly under such stress. The reactors had to be forged from single, hollowed-out ingots of specialized heat-resistant steel. The epicenter of this effort was the Luna Works, located near Merseburg in eastern Germany. To call Luna a factory is an understatement. It was an industrial city, a cathedral of piping and steam stretching over 3 miles in length. By the start of the war, the Luna complex consumed as much electricity as the entire city of Berlin. The site layout was a masterclass in logistical flow, but also a showcase of inefficiency. It took roughly 4 tons of coal to produce just 1 ton of synthetic fuel. The waste was enormous. The plants produced mountains of slag and ash that had to be hauled away constantly, creating gray, artificial hills around the facility that were visible from the air. On one side, trains dumped thousands of tons of lignite, soft brown coal, every single day. This coal was crushed, dried, and mixed with heavy oil to create a thick paste. This paste was then pumped into the high-pressure stalls. Inside the reactors, hydrogen gas was injected. Under the intense heat and crushing pressure, the coal's molecular lattice shattered. The hydrogen forced its way in. The paste turned into a vapor, which was then distilled. Out of the other end of the Luna Works came synthetic gasoline. It even smelled different. German tank crews and pilots noted that their fuel had a distinct, sweet chemical odor, unlike the earthy smell of natural petroleum. It was a synthetic smell for a synthetic war. This was not a cheap process. Producing a gallon of synthetic fuel cost roughly 4 to 5 times more than pumping crude oil out of the ground in Texas or Baku. It was an economic disaster. But in the logic of war, cost is irrelevant. Availability is everything. By 1940, this chemical alchemy was the only thing keeping the Luftwaffe in the air. The outcome of the Battle of Britain relied on fuel that had started its life as a rock in a German mine. At its peak, the German synthetic fuel industry was producing over 100,000 barrels a day. It supplied more than 90% of the aviation gasoline used by the German Air Force. The Allies eventually realized that Luna was the heart of the beast. The plant became the most heavily defended industrial square mile in Europe. It was surrounded by hundreds of heavy flak guns. Smoke generators were installed every few dozen yards. When the air raid sirens wailed, the entire 3-mile complex could vanish under a thick, oily white fog in less than 15 minutes. The engineers at IG Farben had successfully divorced the German war machine from geology, but they had married it to a new vulnerability: infrastructure. These plants were massive, stationary targets. They could not be hidden, and they could not be moved. As long as the skies above them remained clear, the engines would turn. But the moment the bombers arrived, the flow of synthetic blood would stop. Chapter 2: The Diesel Beast. While German engineers were obsessed with complexity, constructing chemical refineries to synthesize high-octane gasoline, their counterparts in the Soviet Union were solving a different problem with brute simplicity. When the German Wehrmacht invaded Russia in 1941, they brought with them thousands of tanks, panzers driven by Maybach engines. These were masterpieces of mechanical precision. They ran on gasoline, the same fuel used by cars and trucks. The German logic was sound. One fuel type simplifies the supply chain. If a tank runs dry, you can siphon gas from a truck. But on the battlefield, gasoline has a fatal flaw. It is volatile. At room temperature, gasoline releases vapors that can ignite from a single spark. When a German panzer was hit by an anti-tank shell, it didn't just break, it often exploded. The crews called their own tanks Ronsons, after the cigarette lighter advertised to light every time. The Soviets took a different path. In the late 1930s, at the Kharkiv locomotive factory in Ukraine, a design team led by Konstantin Chelpan finalized the V2 engine. This was a 12-cylinder beast, water-cooled, displacing nearly 39 liters. But the revolutionary aspect wasn't the size. It was the cycle. The V2 was a diesel engine. For an automotive engineer, the difference between the Otto cycle, gasoline, and the diesel cycle is fundamental. A gasoline engine mixes fuel and air, then ignites it with a spark plug. A diesel engine compresses the air until it is so hot that the fuel ignites spontaneously upon injection. This meant the Soviet tank did not need spark plugs. It did not need a complex ignition system that could fail in the damp Russian mud. But more importantly, diesel fuel is remarkably stable. You can throw a lit match into a bucket of diesel, and the match will likely go out. When a T-34 was penetrated by enemy fire, it was far less likely to turn into a fireball than its German counterpart. This simple chemical reality saved the lives of thousands of Soviet tankers. The engineering of the V2 engine was also a triumph of metallurgy, born of a ruthless strategic calculation. While Western nations were casting heavy iron engine blocks, the Soviets cast the V2 block out of aluminum. This was an expensive, difficult choice for a nation struggling with industrialization. Aluminum was desperately needed for aircraft frames. Yet, the Soviet leadership prioritized the tank engine. They allocated their precious light metals to the ground war. accepting that their planes would have to be made partially of wood and resin. However, the V2 was not a refined machine. German engineers who captured T-34s were horrified by the workmanship. The engine parts were rough, often showing the marks of hand filing. There were no needle bearings, only simple plain bearings. But this looseness was a feature, not a bug. The tight tolerances of a German Maybach engine seized up when dust or grit got into the oil. The loose, rattling Soviet diesel just chewed the grit up and spat out the exhaust. It also solved the nightmare of the Russian winter. In temperatures of minus 30 degrees, batteries die. A gasoline engine with a dead battery is a useless box of steel. The V2 diesel, however, was equipped with a pneumatic starting system. The driver could open a valve from a compressed air cylinder, forcing the pistons down and turning the engine over without a single volt of electricity. The greatest weapon the diesel engine provided was range. Diesel fuel has a higher energy density than gasoline. It contains roughly 10 to 15% more energy per gallon. Furthermore, the diesel cycle is thermally more efficient. A diesel engine converts more of that heat into motion, rather than waste heat. The result was a strategic mismatch. A German Panzer IV could travel roughly 200 kilometers on a road before running dry. A Soviet T-34, running on diesel, could push close to 300 or even 400 kilometers with external drums. This seems like a minor statistic until you look at the map of the Eastern Front. The distances in Russia are vast. The Soviet generals developed a doctrine called deep battle. They didn't just want to break the enemy line. They wanted to drive tanks 100 kilometers behind it to destroy command centers and supply depots. The German gasoline engines, physically, could not support this kind of warfare without a massive, vulnerable tail of fuel trucks. The Soviet diesel engines could. The Germans were so impressed by the V2 that Daimler-Benz actually proposed copying it directly for their own tanks. But they couldn't. The German economy couldn't spare the aluminum to cast the blocks, and they lacked the alloys to build the high-pressure fuel injection pumps at mass scale. The V2 engine was so successful that its DNA is still found in Russian tanks today. It was loud, it smoked, and it vibrated so hard it could shake teeth loose. It had a service life of perhaps 100 hours before needing a rebuild, but that didn't matter. In the meat grinder of the Eastern Front, the average life expectancy of a tank was often less than that. While German engineers were perfecting the chemistry of synthetic gasoline to keep their precision engines humming, the Soviets built a rough aluminum heart that could pump dirty diesel in the freezing cold, allowing the Red Army to drive all the way to Berlin. Chapter 3: Rommel's Calculus. The North African desert is a place where geography usually kills you before the enemy does. In 1942, the war in the desert was not a war of positions. There were no trenches. It was a war of motion, closer to a naval battle than a land campaign. Tanks moved like ships across a dry ocean. And just like ships, if they ran out of fuel, they were dead in the water. General Erwin Rommel, the Desert Fox, is often praised for his tactical genius. But his defeat was not tactical, it was mathematical. Rommel was fighting a war against the odometer. Every mile his panzers advanced east toward Egypt, his supply trucks had to travel a mile further from his primary port in Tripoli. By the time he reached El Alamein, his supply lines stretched over 1,000 miles. It took a truck a week to drive fuel to the front, and crucially, that truck consumed a massive amount of fuel just to make the delivery. It was a logistical snake eating its own tail. But the real tragedy for the British, and the triumph for the Germans, was found in the smallest unit of engineering on the battlefield: the fuel can. The British Army supplied their fuel in a 4-gallon tin container. It was made of thin, tin-plated steel. The manufacturing was cheap, relying on soldered seams and square corners. The soldiers hated it. They called it the flimsy. The flimsy was a structural disaster. When stacked in the back of a bouncing truck driving over rocky desert tracks, the soldered seams would split. The tins at the bottom of the stack would be crushed by the weight of the tins above. The statistics were appalling. British quartermasters estimated that between 30 and 50% of all fuel sent to the front was lost to leakage before it ever reached a tank. Imagine that. For every 10 tankers that risked their lives crossing the submarine-infested Mediterranean, 3 or 4 of them were carrying fuel that would simply soak into the sand. The leaking fuel did more than just vanish. It turned transport trucks into rolling firebombs. A spark from an exhaust pipe could ignite the vapor trailing behind a convoy. The German solution, by contrast, was a masterpiece of industrial design. In 1937, a German engineer named Vinzenz Grunvogel designed the Asterisk Wehrmacht-Einheitskanister Asterisk. The Allies simply called it the Jerry Can. It was engineered not as a package, but as a machine. It was made of 2 halves of stamped steel, welded together with a recessed seam so it couldn't split upon impact. You could drop a jerry can from a 2nd-story window, and it would not leak. The design details were obsessive. The can had 3 handles on top. Why 3? So a soldier could carry 1 full can using the center handle, or 2 empty cans using the outer handles. Or 2 soldiers could carry 1 heavy can between them, holding the outside handles. This allowed for a bucket brigade to refuel tanks rapidly. The spout was wide and included a dedicated breath tube. This meant air could flow in while fuel poured out. A German tanker could empty 20 liters into a Panzer in less than 45 seconds without a funnel. The British flimsy required a funnel, chugged for air, and took minutes to empty. The Jerry can even had an X-shaped indentation stamped into the side walls. This wasn't for decoration. It acted as an expansion joint, allowing the can to swell in the desert heat without bursting, and to contract in the cold desert night without imploding. The Allied soldiers knew the score. They discarded their flimsies at the first opportunity. British and American troops were understanding orders to scavenge German cans whenever they captured a supply dump. It was a strange irony. The Allied advance across Africa was fueled largely by containers designed and built in the Ruhr Valley. By the time the Americans landed in North Africa, they had reverse-engineered the German design. President Roosevelt later remarked that without these cans, the Allies could not have cut across France at the speed they did. Rommel eventually lost at El Alamein because he ran out of gas. His tanks were immobilized, sitting ducks for British artillery. But the British victory was expensive. It was bought with millions of gallons of wasted fuel, spilled onto the desert floor by bad soldering and cheap tin. Chapter 4: The Octane War. While the Desert War was decided by the container, the air war over Europe was decided by the chemistry inside it. In the summer of 1940, during the Battle of Britain, the Royal Air Force and the Luftwaffe were technically evenly matched. The German Messerschmitt Bf 109 and the British Supermarine Spitfire were roughly equal in aerodynamics and armament. But the British had a secret weapon that didn't look like a weapon at all. It was a colorless liquid. At the start of the war, the standard German aviation fuel was 87 octane. This was synthetic fuel, derived from coal. The British, however, had begun importing 100 octane fuel from the United States and the Caribbean. To an engineer, octane is not a measure of power, It is a measure of resistance, specifically resistance to detonation. Inside a high-performance piston engine like the Rolls-Royce Merlin, the fuel-air mixture is compressed by the piston before it ignites. If you compress it too much, the heat of compression causes the fuel to explode prematurely before the spark plug fires. This is called knocking, and it can shatter a piston or melt a valve in seconds. The higher the octane, the more you can compress the fuel without it detonating. And the more you compress it, the more oxygen you can pack into the cylinder, and the bigger the bang when it finally ignites. The British engineers realized that with 100-octane fuel, they could act aggressively. They modified the Merlin engines to use a much higher supercharger boost pressure. They literally forced more air into the engine than the Germans could dare to attempt. The results were physically measurable. Switching from 87 to 100 octane increased the Merlin engine's output by roughly 30%. At sea level, this meant a Spitfire could take off in a shorter distance. But at altitude, where the air is thin, it was the difference between life and death. German pilots were baffled. In 1939, a Messerschmitt could outclimb a Spitfire. By mid-1940, they watched with horror as Spitfires climbed vertically away from them, or accelerated out of a dive with a burst of speed that shouldn't have been mechanically possible. There was a specific mechanism for this: the emergency power gate. On the throttle quadrant of the Spitfire, there was a small wire seal. In a dogfight, if a pilot needed to survive, he could smash the throttle past this stop. This engaged the supercharger to maximum boost. The engine would scream, drinking fuel at a ferocious rate, but for 5 minutes, it turned the Spitfire into a rocket. If a German pilot tried to do the same thing with his 87-octane fuel, his engine would have blown itself apart. The Germans tried to compensate. Lacking the high-quality crude oil to make high-octane gasoline, they turned to chemical injection. They developed systems like MW50, a mixture of methanol and water injected directly into the cylinders. The water cooled the combustion chamber, preventing detonation, while the methanol provided a power kick. It was a brilliant engineering workaround, but it was complex. It required an extra tank, extra piping, and extra weight. The British solution was simpler, better chemistry at the refinery. This advantage came from the United States. American chemical engineers had perfected a process called catalytic cracking, specifically the Howdry process. This allowed refineries to break down heavy crude oil into high-octane aviation spirit on a massive scale. By 1944, the Allies pushed even further, introducing 150-grade fuel. This juice was so potent it was practically corrosive. It fouled spark plugs and eroded valve seats. Engines had to be overhauled 3 times as often. But the trade-off was worth it. It gave Allied fighters a top-speed advantage of nearly 40 miles per hour over late-war German piston fighters. In the end, the Luftwaffe was defeated not just by better pilots or more planes, but by the molecules in their tanks. The German engines were starved of octane, forcing them to fly lower and slower, while the Allies rode a chemical advantage all the way to the ceiling of the sky. Chapter 5: Operation Edelweiss. In the summer of 1942, Adolf Hitler told his generals, "If I do not get the oil of my Kop and Grozny, then I must end this war." This was not hyperbole. It was a statement of inventory. The German synthetic fuel plants were running at maximum capacity, yet they could barely sustain the Luftwaffe. They could not fuel a continental offensive. The Wehrmacht needed crude oil, and they needed it in millions of tons. So they looked south, toward the Caucasus Mountains, toward Baku. This region was the beating heart of the Soviet war machine. 9 out of every 10 barrels of oil used by the Red Army came from these fields. The German plan, code-named Fall Blau Asterisk, was less of a military conquest and more of a hostile corporate takeover. To execute this, the Germans created one of the strangest units of the Second World War. The Technische Brigade Mineraler Asterisk, the Technical Oil Brigade. This was not a combat unit. It was a roving engineering firm heavily armed with rifles. It consisted of nearly 11,000 men. Among them were geologists, petroleum engineers, drillers, and pipe fitters, recruited from the German civilian oil industry. Their baggage train did not carry ammunition. It carried drilling rigs, miles of piping, and heavy pumps. Their orders were unprecedented. They were to follow closely behind the 1st Panzer Army. As soon as a Soviet oil field was captured, they were to rush in, repair the damage, and begin pumping oil directly into the tanks of the advancing German army. In August 1942, the Germans reached Maikop, the most western of the major Soviet oil centers. The technical brigade rushed forward, expecting to find burning wells. What they found was a masterclass in civil engineering sabotage. The Soviet engineers hadn't just set the wells on fire. Putting out a fire is relatively easy. You can use dynamite to blow the oxygen away from the flame. Instead, the retreating Soviets had poured wet concrete down the boreholes. They didn't stop there. They threw down scrap iron, broken drill bits, and twisted piping into the wet cement. For the German engineers, this was a nightmare. To restart production, they couldn't just drill a new hole, because that takes months of geological surveying. They had to drill out the concrete plugs inside the existing steel casings without damaging the casing itself. Imagine trying to drill through reinforced concrete that is harder than the rock around it, while working blindly, thousands of feet underground. Every time the German drill bits hit a piece of Soviet scrap iron embedded in the concrete, the bits shattered. The technical brigade worked for 5 months at Maikop. They shipped in heavy equipment all the way from Austria. In the end, they managed to extract barely 70 tons of oil per day. That was enough to fuel perhaps a single tank regiment for a morning. The desperation produced strange improvisations. German troops stripped church bells for bronze bushings to rebuild seized pumps. Local Soviet engineers, conscripted at gunpoint, pretended to translate well logs while quietly swapping the depth scales to mislead the drillers. In Grozny, NKVD officers had cached replacement blowout preventers in mountain caves so they could reopen fields as soon as the Red Army returned. An underground inventory system that mirrored the German pipe yards marching behind the panzers. The gamble reached the edge of the Black Sea. In September, Brandenburg commandos seized the rail hub at Tuapse long enough to unload an entire train of drilling mud and drill collars. It was a brief victory. Partisan demolition teams blew the mountain passes behind them, stranding the heavy rigs. A German oil officer later wrote, "We had the tools for a refinery on top of a goat trail." Meanwhile, the real prize lay hundreds of miles further south in Baku. The Germans never got there. They were stopped in the mountain passes, but the engineers at Baku had prepared a final, apocalyptic contingency. The Soviet NKVD had prepared a liquid earth policy. They had drilled deep, horizontal shafts between the oil reservoirs and the Caspian Sea. If the German tanks had crested the final ridge, the order would have been given to blow the separating walls. The pressure of the sea would have flooded the reservoirs, ruining the geological formation forever. The Germans fought for geology, but they were defeated by the engineers who understood it best. Chapter 6. General Winter. While the technical brigade struggled with concrete in the south, the main German army in the north ran into a wall of physics. In late 1941, and again in the winters that followed, the temperature on the Eastern Front dropped to -40 degrees. At this temperature, the material properties of the world change. Steel becomes brittle and can shatter like glass. Rubber tires freeze hard and crack. But the most immediate crisis was viscosity. Engine oil is designed to flow. It coats the moving metal parts of an engine to prevent friction. But oil is a fluid, and its viscosity is dictated by temperature. At -40 degrees, standard German mineral oil stopped acting like a fluid and started acting like tar. When a German driver tried to start his Opel truck or his Panzer in the morning, the engine wouldn't turn. The oil had cemented the pistons to the cylinder walls. The friction was so high that the starter motor, powered by a lead-acid battery that had already lost 60% of its amperage due to the cold, would simply burn out. The Wehrmacht found themselves commanding an army of statues. To combat this, German troops resorted to medieval measures. They lit bonfires under the steel bellies of their tanks. The idea was to thaw the oil sump from the outside. This was incredibly dangerous. If the fire was too hot, it could anneal the armor plate, softening the heat-treated steel and making it vulnerable to enemy shells. Worse, the heat could cook off the ammunition stored on the floor of the tank. Many panzers were lost not to enemy fire, but to their own crews trying to wake them up. The Luftwaffe faced an even more paradoxical problem. An aircraft engine needs to be cooled. The BMW 801 engine in the Focke-Wulf 190 used an oil cooler, a radiator where hot oil was exposed to the air. But in the Russian winter, the air was so cold that the oil in the cooler would freeze solid during flight. This created a bizarre contradiction. The engine would overheat and catch fire because the oil meant to cool it was frozen solid in the radiator lines, blocking the flow. German mechanics had to design makeshift baffles and covers to block the freezing air from entering the cooling intakes, intentionally making the cooling system less efficient just to keep the fluid moving. The Soviets, however, were fighting in their own backyard. They understood the cold. Their solution to the viscosity problem was chemical. Standard Red Army procedure in winter was to dilute their engine oil with gasoline. When a Soviet driver parked his T-34 for the night, he would pour gasoline directly into the tank's oil system and run the engine for a few minutes. The gasoline thinned the oil, lowering its viscosity. During the night, the mixture stayed fluid. In the morning, the thin oil allowed the engine to turn over easily. Once the engine reached operating temperature, the volatile gasoline simply evaporated from the hot oil, leaving the heavy lubricant behind to do its job. It was a risky technique. If you added too much gasoline, the oil film would break and the engine would seize. But the Soviets accepted this risk. A seized engine could be replaced. A frozen army could not. The Germans also discovered that their synthetic fuel had a shelf life. The complex chemical soup produced at Luna was not as stable as natural gasoline. In the extreme cold, certain components of the synthetic fuel would separate or crystallize, clogging fuel filters with a waxy sludge. So, while the German army spent hours every morning lighting fires and boiling water to pour over intake manifolds, the Red Army simply turned a valve, hissed compressed air into their diesel cylinders, and rolled forward into the snow. The war was often decided before the first shot was fired, purely by who could get their engine to start. Chapter 7. The Red Ball Express. By August 1944, the Allied armies in France faced a crisis that had nothing to do with German resistance. The German army was retreating faster than the Allies could chase them. But as General George Patton's Third Army raced toward the German border, his tanks suddenly stopped. They didn't stop because of enemy fire. They stopped because the fuel gauges read empty. The Allies had millions of gallons of fuel, but it was all sitting on the beaches of Normandy, 300 miles behind the front lines. The French railway network had been pulverized by Allied bombers before D-Day. It was a ruin of twisted steel and cratered beds. The only way to move fuel was by road. This gave birth to one of the greatest feats of traffic engineering in history, the Red Ball Express. It was a conveyor belt of trucks that never stopped. Army engineers designated 2 parallel highways running from the beaches to the front. One road was exclusively for northbound traffic. The other was exclusively for southbound. They turned public roads into a massive, one-way industrial loop. The rules were simple and brutal. No civilian traffic, no stopping. Speed limit, 25 miles per hour. Convoys were to maintain 60-yard intervals. In reality, the rules were ignored. The drivers, mostly African-American soldiers in segregated units, realized the desperation of the front. They removed the speed governors from their GMC, Deuce and a half trucks. These vehicles, designed to carry 2.5 tons, were routinely overloaded to carry 4 or 5 tons of jerry cans and artillery shells. The wear and tear on the machines was horrific. The trucks were driven 20 hours a day. Engines overheated. Tires literally melted from the friction of the hot asphalt and the relentless load. It was common to see trucks littered along the ditches, not destroyed by mines, but by blown rods and seized transmissions. At its peak, the Red Ball Express employed nearly 6,000 trucks. On a single day, this rolling pipeline delivered over 12,000 tons of supplies. To put that in perspective, that is the weight of an Eiffel Tower moved 300 miles every 24 hours. But trucks consume fuel to deliver fuel. As the supply lines lengthened, the math turned against them. By the time the Red Ball reached the German border, the delivery trucks were consuming nearly half the fuel they were carrying just to make the round trip. To solve this, British engineers launched a project that bordered on science fiction. Operation Pluto, pipeline under the ocean. The idea was to pump fuel directly from England to France across the floor of the English Channel. But laying rigid steel pipe underwater takes months. They didn't have months. They turned to the makers of submarine telegraph cables. They designed a flexible pipe called the HAIS cable. It had a lead core, reinforced with steel tape and armored wire. It looked like a massive electrical cable, but it was hollow. Because it was flexible, it could be coiled. The British Navy converted merchant ships by installing massive drums in their holds. They simply sailed across the channel, unspooling the pipeline off the back of the ship like fishing line. For larger diameter pipes, they built the conundrums. These were gigantic floating bobbins, 30 feet in diameter, looking like enormous sewing spools. A tugboat would tow the bobbin, and the steel pipe would unwind and sink to the sea floor. To hide the pumping stations on the English coast from Luftwaffe reconnaissance, the architects disguised them. A pumping station capable of moving 1 million gallons a day was built inside a fake ice cream parlor. Another was hidden inside a nondescript seaside bungalow, where the garage housed massive diesel pumps instead of a car. Pluto was a slow starter, but eventually it worked. It pumped over 170 million gallons of fuel to the continent. It was the engineering triumph that allowed the Allies to cross the Rhine. Chapter 8: The Suicide Sortie. On the other side of the world, the Empire of Japan was facing the ultimate consequence of an engine-based war. They had no oil. By 1944, the American submarine blockade had effectively severed the shipping lanes from the Dutch East Indies. The oil tankers were sinking. The refineries were dry. The Japanese Imperial Navy, once the terror of the Pacific, was largely anchored in port, rusting, simply because they couldn't afford to turn the screws. Desperation drove the Japanese government to a chemical alternative that defies belief: the Pine Root Campaign. The logic was rooted in basic organic chemistry. Pine trees produce resin. Resin contains turpentine. Turpentine is a hydrocarbon. If you distill it, you can, in theory, run an engine on it. The government mobilized the entire civilian population. They didn't just ask for volunteers, they emptied the schools. Children were sent into the forests to dig up massive pine stumps. The instructions were specific. The roots had to be dug up, chopped into chips, and heated in crude stills. It was a medieval effort for a modern war. The targets were staggering. The government demanded the production of 12,000 barrels of pine oil per day. To achieve this, millions of villagers were digging in the dirt. The distillation process was often done in backyard stills that resembled moonshine operations. The resulting liquid was a crude, pungent oil. It was gold in color and smelled like paint thinner. But an aircraft engine is not a paintbrush. When Japanese engineers tested this pine root oil in standard engines, the results were catastrophic. The fuel had a very low octane rating, leading to immediate knocking. Worse, it was sticky. It contained high levels of gum and resin that the crude distillation couldn't remove. After just a few hours of operation, the pine resin would coat the fuel lines. It would glue the valves shut. It fouled the spark plugs with a thick, varnish-like deposit. Pilots reported that their engines ran rough, vibrated violently, and lost power unpredictably. The exhaust fumes were acrid and stinging. This fuel was reserved for the only mission profile that could accept a short engine life: the kamikaze. The logic was grim. A kamikaze plane did not need an engine that would last for 500 hours. It only needed an engine that would last for 2 hours. It didn't need to fly home. But the pine root oil was so poor that many of these pilots never even saw the American fleet. Mechanics noted that the volatile fuel eroded the rubber seals in the fuel tanks. On the runway, planes would leak this turpentine mixture. Since the flash point was unpredictable, fires on takeoff were common. There are records of squadrons taking off to defend the homeland, only to have half their planes turn back or crash into the sea because their engines simply choked to death on the resinous fuel. The Japanese even tried to mix the pine oil with alcohol derived from sweet potatoes. It didn't help. The mixture was hygroscopic. It absorbed water from the humid Pacific air, which further destroyed the combustion cycle. In the end, the Pine Root Campaign was a tragedy of engineering. It required the back-breaking labor of an entire generation of children to produce a fuel that did more damage to their own planes than the enemy could. It was the final, choking gasp of an industrial power that had run out of geology. Chapter 9: The Jet Fuel Compromise. In the autumn of 1944, Allied pilots over Germany reported seeing something that shouldn't exist. It was a plane without a propeller. It moved at speeds that made the fastest P-51 Mustang look like it was standing still. This was the Messerschmitt Me 262, the world's first operational jet fighter. To the Allied pilots, it looked like the future. To the German engineers, it looked like a compromise. The Me-262 was powered by two Junkers Jumo 4 engines. From an aerodynamic perspective, these engines were a triumph. But from a materials science perspective, they were a disaster waiting to happen. By this stage of the war, Germany had run out of the rare earth metals required to build high-performance turbines. They had no nickel. They had no chromium. These are the metals you need to stop steel from melting or deforming under extreme heat. Without these alloys, the turbine blades of the Jumo engine should have melted instantly. The exhaust gas temperature exceeded 800 degrees Celsius. Standard steel turns soft as butter at that temperature. The chief engineer, Anselme France, solved this with a brilliant piece of structural architecture. He designed the turbine blades to be hollow. Inside the engine, he diverted cold air from the compressor to flow asterisk through the inside of the hot metal blades, cooling them from the inside out. It was the same principle as a water-cooled machine gun, but using air at 6,000 RPM. But the real engineering miracle, and the curse, was the fuel. The Luftwaffe could no longer produce enough high-octane gasoline for piston engines. The hydrogenation plants were being bombed into ruin, but the jet engine offered a loophole. A jet engine does not rely on compression ignition like a diesel, nor does it rely on spark timing like a gasoline engine. It is essentially a continuous explosion. You can burn almost anything in it, provided it burns hot enough. So the Germans created J2. J2 was not gasoline. It was a heavy, oily distillate derived from coal tar and diesel oil. It was cheap to make. It was relatively easy to synthesize from the lowest grade of coal, and critically, it was available. However, J2 was dirty. It burned with a heavy, greasy soot. It had a high flash point, which made it incredibly difficult to ignite. To start the Me-262, the pilot needed a small two-stroke starter motor, essentially a lawnmower engine built into the jet intake, just to get the turbine spinning. Then, he had to use a separate tank of gasoline to light the fire. Only once the engine was roaring could he switch the fuel valve to the J2 supply. The pilot had to be a surgeon with the throttle. The fuel control unit was primitive. If the pilot pushed the throttle forward too quickly, the dump of heavy J2 fuel would flood the combustion chamber. The fire would grow faster than the air could cool it. The result was a flame-out or a meltdown. The turbine blades, made of that inferior steel, would simply liquefy and shoot out the back of the engine. The lifespan of a Jumo 4 engine was shocking. A modern jet engine lasts for thousands of hours. The Jumo 4 was rated for just 10 hours of service. In combat conditions, many failed after just 4. Think about that. The most advanced aircraft in history, capable of 540 miles per hour, was powered by an engine that was effectively disposable. It changed the architecture of the air bases. The Germans couldn't just refuel the planes, they had to swap the engines constantly. The hangars became assembly lines. Ground crews learned a choreography. 2 crews with chain hoists could drop a dead Jumo 4 in under an hour and hang a refurbished core the next. Spare engines arrived still warm from test stands, paint bubbling on the exhaust cones. The aircraft sometimes took off with mismatched thrust ratings, one green engine and one that already had 6 hours of fatigue, because there was no time to balance the pair. There were surreal side effects. To save scarce ignition gasoline, pilots used compressed air cartridges to spin the built-in Riedel starter engines, then coasted downhill on perimeter roads to get airflow through the intakes before lighting the J2. In Bavaria, A Me-262 test pilot named Hans Fay defected to the Allies with his jet, partly because he doubted he'd ever be given enough fuel to learn how to fight with it. His surrendered aircraft became a training aid for Allied engineers trying to decipher J-2's soot and sulfur smell. But when it worked, it was untouchable. The J-2 fuel, dirty as it was, provided the caloric energy to push the Me-262 beyond the laws of piston aerodynamics. The Allies had no answer to the speed, but they didn't need one. They just had to wait for the engines to melt. Chapter 10: The Dry Tanks. In the winter of 1944, the war ended not with a bang, but with a gauge reading empty. The Allies had finally shifted their strategic bombing doctrine. For years, they had bombed cities, hopping to break morale. It didn't work. Then they bombed ball-bearing factories. The Germans just imported bearings from Switzerland. Finally, General Karl Spaatz and the Strategic Bombing Survey looked at the chemistry. They realized that while a tank can drive without a ball bearing, it cannot drive without fuel. They launched the oil plan. They sent thousands of bombers to Luna, Perlitz, and Blechhammer. They didn't just bomb the buildings, they bombed the pipe racks. They bombed the rail lines feeding the coal. The reaction from the Nazi hierarchy was frantic. They launched the *Jahlenberg program *, an architectural frenzy to move the fuel industry underground. They employed tens of thousands of slave laborers to hollow out caves in the Harz Mountains. They built small, primitive distillation columns called ofen, ovens, hidden in forests and gullies. It was the industrial equivalent of a dying animal burrowing into the ground. But you cannot hide a refinery that needs 4,000 tons of coal a day. The logistics were impossible. The climax of this tragedy occurred in the Ardennes forest in December 1944, the Battle of the Bulge. This was Hitler's last gamble. He assembled the 6th Panzer Army for a massive strike toward Antwerp. The spearhead of this attack was the King Tiger, the Tiger II. To a mechanical engineer, the King Tiger was a masterpiece of excess. It weighed 70 tons. It carried an 88mm cannon that could slice through any Allied tank from a mile away. Its frontal armor was 150mm thick. But the engineering flaw was the consumption. The King Tiger was powered by a Maybach HL 230 engine, the same engine used in the much lighter Panther tank. It was woefully underpowered for 70 tons. The fuel economy was catastrophic. Cross-country, a King Tiger consumed 5 gallons of fuel for every single mile it traveled. It had a range of barely 50 miles off-road. The German battle plan explicitly stated that the offensive could not succeed with the fuel they had on hand. The orders given to Commander Jochen Paper were clear. He had to capture American fuel dumps to keep moving. He was fighting a war of scavenging. It didn't work. As the Americans realized what was happening, they burned their own supply depots. They poured thousands of gallons of gasoline into the snow and lit it, creating walls of fire to deny the Germans the liquid they needed. The result was a graveyard of engineering. When the snow cleared in January, American troops walked through the Ardennes and found hundreds of German vehicles abandoned. They found King Tigers, the most fearsome fighting machines of the war, sitting silently on the sides of the road. They weren't destroyed. There were no shell holes in them. The crews had simply opened the hatches, drained the last dregs of fuel to blow up the internal demolition charges, and walked home. The Luftwaffe suffered the same fate. By 1945, Germany had thousands of fighter planes. They had jet fighters, but they had no pilots who knew how to fly them. Why? Because flight training requires fuel. To train a pilot takes hundreds of hours of flight time. The Luftwaffe had cut training hours to the bone to save gas. They were sending teenagers into the cockpit who had barely 10 hours of experience. They knew how to take off, but they didn't know how to fight. In the final weeks of the war, Allied fighters would strafe German airfields. They would see rows of Me-262 jets parked on the tarmac, perfectly intact. They sat there like museum pieces. The tanker trucks next to them were dry. The Second World War was not merely a clash of ideologies. It was a contest of thermodynamics. It was the first conflict in human history where the outcome was decided strictly by the global flow of hydrocarbons. Consider the physics. A single gallon of gasoline contains roughly 31,000 kilocalories of potential energy. That is more raw power than is contained in 80 pounds of TNT. The Allies won not simply because they had better generals, but because they controlled the calorie count. Between 1939 and 1945, the United States alone produced over 6 billion barrels of oil. Germany produced less than 5% of that volume, and they did so at a chemical and electrical cost that cannibalized their own infrastructure. The lesson left for the engineers of the 20th century was written in the silence of those abandoned king tigers. You can build the most advanced machine in the world, but if you cannot feed it, it is nothing more than a statue of steel.